Welcome everyone for this session in MASTERCLASS. Today we have a pleasure with Xavier Lamy to speak about weak solutions and selection principles, especially for the Wolbert equation.
Okay, thank you very much. So this talk is going to be about this equation, du dt plus ddx of u squared over 2 equals 0. So here u is a function of time and space. Time is positive, we start from 0 and we evolve, and x is a variable in R. So this is a partial differential equation. It's one of the simplest nonlinear partial differential equations, but I hope I will be able to convince you that even though it's quite simple, there are quite deep things happening that are a very good example to understand many, many notions in this world of partial differential equations. So I want to start by telling you a little bit about where this equation comes from. So it can be used to model some physical phenomena. And the reason I want to tell you about it is because you will see that this will be a guide for the mathematical understanding of this equation. So basically it's a model for a simplified model for different things. But for instance, it can be used to model traffic flow or like some simplified fluid motion. And the idea is that, okay, we have this 1D container with like some particles that are flowing in it. And if you're thinking about traffic, maybe there are like vehicles that can evolve in time. They try to advance. And okay, you can model that kind of stuff by saying, okay, there is a function at fixed time t. There is a function rho of tx, which is the concentration of particles or vehicles at time t and position x. Okay. And let's say this thing is flowing, so you have like some velocity also at time t and position x. So what does it mean? When I say concentration of particles, it means that when I do the integral of rho of tx dx between a and b, say I have a here, b here. So you see this integral is just the area under the curve. This represents the quantity of particles that I have in that part of space. Okay? And if you want to understand how your fluid or how your traffic is evolving, what you want to understand is how this thing here evolves with time, right? The derivative of that quantity with respect to time. Now, what can you say? Well, how does it evolve? It depends only on what is going out of this box on the side B and what is entering from the left on the side A, right? So what's entering you call J of A, and what's going out from B you call J of B, and here J is going to be a physical quantity that is the current, and that is actually defined exactly like I said. Like it's just telling you how much is exiting or entering from both sides. So of course, I mean, you need to understand what this current is doing. And okay, the natural thing to expect is that actually it's just the concentration of molecules, of particles, multiplied by the velocity, right? This is what's exiting on the right. This is what's entering on the left. Actually, it's sometimes not as simple as that. There can also be, like this is an average velocity, and there can also be an effect that is called diffusion, which is the fact that the particles, they have a tendency to spread. Like there is a small, like, tiny motion of them, and they have a tendency to spread. So say if you are at a point like that where there were more particles here on the left, then they will want to move a little bit from the right independently of the global velocity of the field. But anyway, that effect is very small. So for now, so this is called the diffusion. But for now, we are going to assume that epsilon is equal to 0 to simplify everything. But you will see that later on, we will need to remember that there was this effect. Okay. Now let's see, what's the relationship between this equation and that here? Well, you can decide to differentiate this equation with respect to b, right? Why not? You take a derivative with respect to b, and you know that when you derivate this with respect to b, you just find rho at time t and at position b, right? This is the fundamental theorem of calculus. So what you get when you do that is that, okay, you get d rho dt, because here I get rho, but there still was the d dt here. And then here, this is a constant with respect to b, and here I will get minus dj with respect to its second variable. So I will get this, right? Which I can rephrase like this. D rho dt plus d dx of rho times v equal to 0. Okay, so that's basically, it's called the continuity equation. That's the equation satisfied by basically any fluid. And now you need to make some assumption on your model. You need to say, okay, but what's this v? What do you know about it? So this is a modeling assumption. And then you have various choices that you can make. But there are some quite natural choices. You could say, okay, but v is going to be proportional to the quantity of particles I have. Say the more particles, the faster they flow. Why not? And then if you do this, your j is going to be just c times rho squared. Or if you think about traffic, like about vehicles, what is going to happen is that if you have too many particles, too many vehicles, at some point they are stuck and they won't flow anymore. So you have a maximal velocity above which you cannot really go. So that would be a v that looks like that. And then your j would be of the form rho times v max minus 0. So you see that in both cases, j as a function of rho is just a parabola. It's a second degree polynomial, right? So after a change of variable, all parabolas, they look the same. That's why we look at this equation exactly. So we call our new variable that we have done some transformation about u, and we get du dt plus d dx of u squared over 2 equals 0. This is just one specific choice of a parabola, but they're all the same once you change variables. Okay, so you could say, why am I telling you that? In fact, we don't really need to understand this in order to study this equation mathematically, but you will see that it will be important. So for the first part, it's not going to be so important. We want to understand classical solutions. What do I mean by classical solutions? Basically, you assume that all these derivatives that I wrote down, I mean, they make sense. You have like a function that is really differentiable. So say u of tx is a function that is c1, say, on some time interval and on r. And then you write du dt You can even apply the chain rule and say that d dx of u squared over 2 is like u times du dx equal to 0. And you want to understand an evolution, so say you put some initial condition. Okay, this is a C1 function. Can we understand the evolution that is dictated by this equation? So if it's really like a good physical equation, you should be able to say, well, if I know the initial condition, I'm going to be able to predict how the system evolves, right? So I'm going to draw a lot of pictures. So here, you could have x here, and say you have your function u0 of x, and then let's say you have an arrow of time that you think about it in the depths of the blackboard, like perpendicular to the blackboard, and you want to know, well, if I fix a later time, how has my things evolved? Okay, can I understand the graph of u of tx at this later time? Okay, and sometimes, I mean, you see this is a 3D picture. It's going to be a bit hard to make sense of sometimes. Sometimes what I will do is I will only draw the projection onto this plane here. I will only try to explain what happens in the space x and t. And for instance, the type of stuff you would like to understand is, okay, what if I fix like a curve, say x equals capital X of t, and I want to understand if I know the solution here, am I able to understand what it does along this curve? Okay, so in some sense, this is how you want to solve your equation. So if you want to understand the evolution along a curve, say, and you know it starts from a point x0, what do you do? Well, you look at u at t, x and t, right? And you differentiate it. Okay, so let's do that. When you differentiate it, you apply the chain rule. You will get du dt at t and x. And then here you need to differentiate x and then u. Plus x prime of t du dx at tx. Well, in general, okay, maybe there is not much you can say about that, but you see that there is a very good choice of x that would make things super nice, is if this x prime is just u. Okay? So if x prime of t is equal to t u of t and x of t, then you see that I can use my equation, and then this is simply 0. Okay, very nice. So what you understand is then u of t xt is just going to be constant, equal to its value at time 0. There was a question here, maybe. No? Okay, so this is pretty nice. If we are along a curve that satisfies some differential equation, then in fact you know that the function u, it has to stay constant. And in fact it's even better than that. Now that we know that the function u is constant, in fact this curve is very simple. It's just x prime equals a constant. So in fact now we go back and we realize that x prime is a constant, so in fact x of t was just x0 plus u0 at x0 times t. Okay. So let's try to make a picture of what we learned. Right? We have, say, a point x0 here. We know that the initial condition, it has some value here. Then we draw the line x equals x0 plus u0 of x0 t. And we know that along that line, the value of u is equal to u0 of x0. Okay, this is exactly the calculation we just did. So we know that in fact, starting from the initial condition, we can know exactly what the function u does provided we go along this line that is given, the slope of which is given by the initial value. So, I mean, it's very good. Now we take any point here, redraw the line, and we know exactly what u does. And we can do that for every point, so that's it. We have solved the equation. Okay, but it's not so simple. Imagine that here, so here I have my u0 of x0, here I have my u0 of x1, and those, they give me the slopes of my line. Now imagine that here the value was larger. Now what's going to happen? If it's larger, it means the slope of this one does not go as far to the right as this one, so at some point it's going to cross it. So you see, here it means that here the solution at this point, it should have this value, because it's constant along this one, but it should also have this value, so it's just impossible. So here, what happens here is that I would call a shock. Somehow you would like your solution to have two different values, and that's not possible. So in fact, what we have shown is that classical solutions, if they exist, we know what they do, but in general, they won't exist. I mean, this is just impossible. This cannot happen. Maybe it's interesting to spend a little bit more time understanding, I mean, why this has happened, maybe on that type of picture. And in fact, this is, I don't know who chose the picture that was on the poster, but this is exactly the picture that goes with what I'm going to explain now. Say, okay, you have u0 of x, it's given like that. And now I have a point x0 here, a point x1 here, and you see I am exactly in this situation where the value of u0 at x0 is larger than the value of u0 at x1. Now, what this picture is telling me is that, in fact, to understand what happens to this point on the graph, it is moving at velocity. So after some time t, it's going to be moving by this distance that is going to be u0 of x0. This is the slope of this line times the amount of time it goes there. And here you see that this one is going to be moving too, but with a smaller velocity. So what happens after time t? What happens, you know, if I move all my elements of the graph, is that this point, it has moved further to the right than this point. So you see maybe something that looks like that. And here you're not happy at all, because this is not the graph of a function, okay? Okay? If you look at a point here, well, you would need to have like 3 different values. This cannot happen. I mean, you cannot write this as u of tx. So in fact, those are just, this picture and this picture are just 2 ways of looking at the same problem. Somehow, if I want smooth solutions, my equation is going to make something impossible happen at a certain point. So what does it mean? It could mean, well, okay, we've lost. Let's forget about this equation. It's no good. But it could also mean that our notion of solution is not the right one, and that we need to use a weaker notion of solution that does not make that kind of assumption. So in fact, this is what we're going to do. This is, say, part 3 of my talk. Weak solutions. And here, what's good to do is to recall, I mean, where does that equation come from? It had a physical meaning, right? And in fact, that physical meaning, it was the one up there, right? It was this thing of the evolution of this quantity of particles between space A and B. And then we did the derivative of that thing, and we obtained that other equation, the one that we use for classical solutions. But in fact, I mean, the physical meaning of the problem was already a weaker notion of solution. It was just telling us how that quantity evolves, right? So it was just telling us d dt of integral between a and b utx dx should be equal to u squared over 2 at time t space a minus u squared over 2 at times t space b, which, let me write it as minus u squared over 2 between a and b. Okay? And in fact, I mean, for this, you don't really need to speak too much about derivatives to make sense of this. I mean, you have this derivative, but after an integration, so maybe you can still make sense of some solutions that are not C1, okay? And in fact, this is the actual meaning of the equation. The equation was actually not that one. It was that one, if you think about it, if you think about the modeling. So here, in some sense, the weak solutions, it's not just a mathematical trick. It's actually, I mean, how you should describe the evolution if you want to stick to its physical meaning. Okay, so let's see if we can understand a little bit these weak solutions. Let me first make a small remark. If U is C1 and it is a solution of this, then it's going to be a classical solution. Okay, why? Well, this is what we did before. You just take derivatives with respect to B and you obtain exactly our equation. So in some sense, we have lost no information with respect to classical solution, because if we look at this constraint and we live in the world of C1 functions, then it's telling us exactly the same thing. Now the hope is that we can understand some other types of solutions that do not have this constraint here. So this is what I want to convince you of, is that now this equation written in this weak sense, it makes sense even if there is some kind of discontinuity. Okay, even if there is a shock. So let's try to understand that claim a little bit better. Let's imagine we have x and t. So again, I'm doing my projection into the xt space. And let's imagine we have, okay, some curve, let's call it x equal capital Y of t, along which there is a shock. On the left, I have a classical solution. On the right, I have a classical solution. And here, I want it to be discontinuous in some sense. Well, what is the simplest example of a classical solution? It's a constant solution. You take a constant, you put it in the equation, it gives you 0. That's fine. So let's start with this very simple calculation. Let's take here on the left a constant solution. Let's call it u minus. So this is for x, which is smaller than y of t. And here, let's take another constant solution. Let's call it u plus for x, which is larger than y of t. Okay, and let's try to understand, okay, can I give a condition, say on these curves, on these numbers here, so that I solve this equation here. Okay, so let's fix a time t. Let's fix A, let's fix B. And we need to look at the integral of our solution on that interval here. Okay, so let's do that. The integral from a to b of u of tx dx, well, it's just gonna be the integral from a to y of t of u minus plus the integral from y of t to b of u plus, right? Okay, you just use like the shall relationship, you split the integral into two, and now on the left you have your constant classical solution, on the right also. Now the good news is that you know how to differentiate this, right? So if you do d dt of that thing, and I'm sorry, I should have given more space here, otherwise it becomes a mess. If you d dt of that thing, well, okay, u minus is a constant, so this is just u minus times the size of the interval, and what you get is just y prime of t times u minus minus y prime of t times u plus. Okay? And you want this to be equal to that, to u squared over 2 at a. So here you use the weak equation and you say, wait, it has to be like the value of u squared over 2 at a. So this is just u minus squared over 2 minus the value of u squared over 2 at b. Okay, so maybe you can write this as, see here you can do u minus minus u plus, you can factorize it here also. So this is u minus plus u plus over 2 times u minus minus u plus. And then you can simplify by u minus minus u plus, and you arrive at the condition that y prime of t should be equal to the average of the values on both sides. Okay, so now you have admissible solutions of our problem that are not continuous. Okay, they have like different values on both sides of a curve. And this curve, in that case, it just needs to be a line with a constant slope that should be the average of u on both sides. Now, okay, here we did like the very simple case of a solution that is just equal to two different constants on two sides of a curve. But okay, you can generalize that, and I'm not going to do the calculations, but they are not so hard to make. In general, you will have weak solutions which are of the following form. So I'm just going to do a picture. Okay, I have time t, I have space x. Say I start with a smooth solution, and then it could happen that here my characteristics, okay, they meet at some point. Right, this was my first picture. Like if I have like here u0 of x0 larger than u0 of x1, I said I'm going to create a shock. Well, what's going to happen here is that now I'm going to have a shock curve, okay, which is going to have the property that its local slope, okay, the way it's tangent, it should be the average of the values from both sides. And we know that the values from both sides, they are characterized by these characteristics. So I'm just saying basically like these two characteristics at which you have a shock created, they should arrive at the curve with the same angle from both sides. So somehow there is like a very geometric representation of what it means to be a weak solution. And then of course you could have this situation everywhere. You could have like a lot of shock curves, and this is gonna be giving you like a good notion of solution that satisfies this. And now what we have won is that you can prove existence. So actually you have existence of weak solutions for all times in the future. So you see, when we were looking at classical solutions, we were stuck. There is a time at which you create a shock, there is no classical solution anymore. Now we kind of widened the concept of solution, and now I'm claiming, I did not show it to you, but with that widened, weak concept of solution, you can actually prove that there exists a solution for all time. So at this point, you're quite happy, right? This is a physical system. You could predict the evolution in time. So you could say it's the end of the story, but it's not. Because, okay, it's fine to have existence of a solution, but in fact, if you really want to say that you were able to predict the evolution of the physical system, you need to have uniqueness of the solution. Okay, otherwise, I mean, you're not making any sense. And so you need to ask yourself the question, well, this weak solution that I have found, is it unique? Of course, the answer is no. Otherwise, it would be too easy, right? So let me give you a simple example. Let's say, okay, so I'm always doing my pictures like with space and time. Let's say you have a solution here that say my initial data were equal to +1 on the left, -1 on the right, and say here it does whatever you want between -1 and +1, then you know that here, okay, you have your characteristics like that, here you have your characteristics like that, here you're creating a shock. Okay, so what you could do is put a shock here, here you take u equal +1, here you take u equal -1, and you see that the average of these two values, it is 0, this is the slope of my curve. You're happy, you have your weak solution. Now let me show you another weak solution with the exact same initial conditions. So you start the same. So here you have +1 on the left, you have -1 on the right. Here you would like to create a shock, but you could also create any type of artificial shock, like you could have +1 here, -1 here, say +2 here, and -2 here. Okay, so it means you would have new shocks, one here, one here, one here, and you just need to make sure that the slope of these shocks, they correspond to the averages of your values here. Okay, so here +1 -2, it's -1, this is the slope -1/2, this is the slope +1/2, and here the average is 0, I have this slope 0. So you see, here is another weak solution with the same initial condition. So this is very bad. I mean, physically, you need to choose. It's only one thing is going to happen. So we thought we were happy, but we're actually not. Now we have this huge class of weak solutions, and we need to choose one from them. And we need to choose one that makes sense, right? It's not just like pick one at random. We need to understand, I mean, what is the evolution of the system actually doing. So that's the second part of my title. What you want is a selection principle. What do I mean by that? Among all your weak solutions, can we select a single one that actually describes what you want to describe? So, okay, what you want to describe, I mean, in fact, it could even depend on what you actually want to describe. Okay, so in I gave you like some example of modeling that is related to that equation. So we're going to try to understand, if you take this model, I mean, what is the correct weak solution to choose? So remember when we were stuck the first time with our classical solutions that did not exist, what we did is we went back to the physical derivation of the equation in order to understand, I mean, okay, what is the actual sense of the equation? Now let's do that once again, and let's recall the physical model. And now let's recall that there was a small parameter epsilon that I said, okay, we're going to take it 0, it's very small anyway. Okay, this was this small diffusion parameter. So actually my equation was not the one I wrote. It was the other one with this epsilon that was very small. So let's write it again. You have du dt plus u du dx. And then if you did like the derivatives in the way I presented in the first time, what you will end up with is du squared over dx squared, d squared u dx squared. Okay, and here I just acted as if all the derivatives are well defined, etc. But in fact, when you have this small positive epsilon, then it is true. Then you do have classical solutions which exist for all time positive. So how is it possible? Like I have my very small epsilon and it looks a lot like my previous equation, and now I can have classical solution. Well, I'm not gonna prove you this, but I'm just gonna make a picture. If you have, say, a shock at the level of the weak solution, say, actually what you see in this equation is really something smooth. It's something that will do a little bit like that. And here there's going to be a length scale that is of the order of square root epsilon. So if you think about the dimensions of your objects here, it's clear that square root epsilon is the only length scale in your system. So if your shocks are going to be widened at some scale, it has to be square root epsilon. What does it mean? It means that here, actually, I have derivatives from my solution, but just they can be very large, right? Typically, if I have to go from, say, 1 to -1 over space square root epsilon, I'm going to have like du dx is going to be over the 1 over square root epsilon. Okay? So what's going on here is that here you have classical solutions for every epsilon, but when epsilon is very small, their derivatives might blow up. So that's why when you send epsilon to 0, in fact, they're not smooth anymore. They don't have derivatives anymore. Okay, so that's something, but how is it helping us with our selection principle? Let's see. So let's try to come back to our weak equation and trying to understand it a little bit better. So it came from d dt of the integral of u between a and b plus u squared over 2 the value at b minus the value at a. So this was the equation we wrote before. And then we wrote equals 0, but now if we have an epsilon, what does it become? Well, you have to integrate this from a to b, so you will get epsilon times the value of du dx between a and b. Now, if you remember that du dx you expect it to be over the 1 over square root epsilon, this is still very small. This is something that will go to 0 as epsilon goes to 0, right? So in some sense, by doing this, we recovered our weak equation. But now when you have classical solution, there is another game you can play. You could say, well, let's try to understand derivatives of other quantities. And let me put u squared over 2. Now, what happens when you derivate this? Say you're allowed to derivate inside the integral, you're going to have u times du dt. Okay? So that's if everything is smooth, of course. But here everything is smooth because I claim there are classical solutions. So there is u times du dt, then you can express du dt in terms of the rest, and you get an equation. So I'm not going to do the calculation in front of you. But what you get is this, okay? So this is what is going to come from this term, basically because u times du dt, you're going to have now u squared times du dx, which is exactly d dx of u cubed over 3. And now what you're going to have on the other side is, okay, again something that is going to 0 and something else. So here you have to believe me. I mean, you have or to do the calculation yourself. You take 2 minutes and you do it. And this is what you get. Now, again, this thing you see, u is over the 1. Du dx is over the 1 over square root epsilon. So this whole thing, epsilon times 1 over square root epsilon, this is going to go to 0 as epsilon go to 0. But now what's going on here? Here you have something that is now of order 1 over epsilon because you have a square. And now you see it does not go, at least not obviously, it does not go to 0 anymore. So in fact, this is telling you actually this bit of information, it has to stay in the limit. Okay? And what kind of information does it give you? It just gives you the information that, okay, it does not go to 0, but at least it has a sign. And in fact, the information that you get from this is that you should impose an extra condition on your weak solution, which is that this thing here is non-positive. So d dt integral from a to b u squared over 2 dx plus u cubed over 3 between a and b. You should impose that this is negative because this is what you get from here. In general, you cannot expect this to be 0. And now there is an important theorem that if you impose this, then you do get uniqueness of weak solutions. This is a theorem by Khrushchev in the 70s. Okay, I'm not going to give you the proof of it, but somehow this is this very important information that if you ask this type of information in addition to your weak equation, which was just this equal to 0, then actually you do get a single evolution, and you see it is consistent with your model when you add the diffusion. So now you're happy again, right? I mean, you're happy, I am happy. Maybe you're not so happy because this is a bit mysterious, so maybe let's spend some time trying to understand what exactly are we asking on our weak solution. Can we understand this on that picture? Okay, basically you can do the same type of calculations I did before, and I'm not going to do them, but I'm going to tell you what's the outcome. The outcome is that basically only the negative shocks are allowed. What does it mean is that I can do a shock like that, so with a u minus on this side that is larger than the u plus on the right side. This is a type of solution that is going to satisfy this. But if you want to do it the other way, so a u minus less than a u plus, this is not allowed. Okay, this is not allowed. Okay, this is just, I mean, you do the same thing we did before. Now you write that there is this inequality, and you realize that if you want that inequality to be satisfied, you should have u minus larger than u plus. Now, if you think about our example here, you see here on the left it's plus 1, on the right it's minus 1, so it's fine. I mean, it's going from something big on the left to something small on the right. This is a jump that is admissible. But this one is not at all, because I'm jumping from something big to something small to something big to something small. So in fact, what it's telling me is that all the solutions where I added this type of weird intermediate jumps, they are not allowed. They are not physical. Okay? If you come from this model with small diffusion, then you will not see them. Okay? So this is, okay, on this example, now we're happy. We see that there is really a unique solution in some sense. And the deep theorem of Khrushchev is to realize that this is also valid when you have complicated pictures like that. Let's see. Let me try to elaborate a little bit more on this condition again. Remember, I did this picture before, right? That if I start like that, my particles on top are going to be moving faster than my particles on the bottom. And so I'm going to see something like that. Okay? So let's say you want to do like a numerical scheme to calculate your solution. You're going to take a small time step, and at some time step, you're going to see something like that. What do you do there? Well, you say, okay, I just replace this by a shock. This part here, I move it back here, and now I just see something like that. It's a shock, right? But if you do that, since it's always the particles on top that move faster, the only shocks you are going to create are ones like that go from top to bottom. You will never create shocks that do the opposite thing, that do something like that. So in some sense, if you think about this interpretation, it is clear that the only shocks you want to see are ones where you are higher on the left than on the right. So this is all consistent. This all makes sense. So okay, now it looks like we are really happy, like we really understood everything. And now this is where there is work for you, because I'm going to tell you about some open questions around these things. Do you have like 2 or 3 more minutes? Okay, so remember we had this equation du dt plus u du dx equals epsilon second derivatives of u with respect to x. And okay, let's call it u epsilon since it depends on epsilon. Okay, I have my evolution u epsilon of tx. Okay, this is a nice equation. We saw that it helped us like make sense of this whole theory. But no, in real life, in fact, you never have an exact equation like that. Things are never equal. There is always some kind of noise, some kind of random noise. Okay? And now you enter the realm of probability, right? Now you have like a random solution that comes with a random noise, and you want to understand statistically how it behaves. Okay, and the type of stuff you can say is that if somehow the noise goes to 0 as epsilon goes to 0, this you will have to interpret in a very specific way. Then you can say that the probability that u epsilon looks very much like your Khrushchev solution, it's going to be very close to 1. Okay, so somehow this is all consistent with the previous story. But you may say, well, okay, that's very nice, but I would like to have precise estimates on that probability. And now this is the stuff we cannot do. So the question is, can we estimate the rate of convergence of this type of stuff as epsilon go to 0? And in fact, it's better to think of it as the stuff that is not close to 1, but is close to 0. So the probability that the distance between u and my Khrushchev solution that this distance is larger, say, than a delta strictly positive. I mean, if you believe what I said, this should go to 0 as epsilon go to 0, but we really would like to have some estimates on this. So this is a part of probability theory that's called large deviations, which is telling you, okay, I have a process that I know converges in some weak sense to a well-identified limit, and now I would like to understand, well, okay, but can I make this a bit more quantitative? A little bit like, say, the central limit theorem is making more quantitative, say, the law of large numbers, if you want. And okay, this is open. This question has no known full answer yet. it's actually super hard because you need to be looking at solutions that are not the Kruskov solutions, and you have an infinity of them. They can be very nasty. So I hope one of you will solve it someday, and I'm gonna stop here. I'm done.
Other questions? In one part of the lecture, we talk about the frame. So
About what?
the frame. So why is u is the order 1 and du over dx is the order 1 over square root of
This picture here, right?
yes.
Mm-hmm.
Why?
So okay, why? You would need a proof, and in fact, it's not even true like that. But somehow the reason for this is that that epsilon, when you look at dimensional analysis, its dimension is a length squared. Why? Because if you want to be able to write epsilon times d dx squared, somehow this has the dimension of 1 over length squared. So physically, this is 1 over length squared. You need this to compensate it. So you need epsilon to be a length squared. So it means that square root epsilon is a length, and this is the only length scale in your system over which you have room to play. Like the point is, it introduces a length scale, and this is the heuristic reason why you expect that a shock, it will become a shock regularized at this length scale. This is not a proof. This is like a very heuristic explanation for why you expect things to be like that. Then, I mean, you actually need to prove theorems. They are not so hard, but not so easy. And I mean, it would be another full lecture, I guess. So.
Juste dans le théorème de Kruskov, est-ce que si on avait juste la condition que ça soit positif, on aurait une unicité?
Alors, si on met positif, ce qu'on va pouvoir faire, c'est en fait inverser le sens du temps et obtenir des solutions à partir d'un temps zéro et aller vers moins l'infini. Et là, on aura existence et unicité. Mais si on veut positif, en fait, et qu'on veut partir dans le futur, il n'y aura juste pas existence. Il y aura des conditions initiales qui n'auront pas d'évolution avec positif. Donc c'est vraiment important que ça soit négatif ici. Et ça se voit en fait ici, que ce n'était pas un truc vraiment de choix entre deux options et l'une est aussi bonne que l'autre. C'est que vous voyez, quand on regarde ça, ça choisit vraiment les chocs qui sont de cette forme-là et pas d'une forme où il faut monter. Ouais. Donc en fait, qu'est-ce qu'il faut faire? Donc cette inégalité, comment est-ce qu'on l'a obtenue? On l'a obtenue en raisonnant sur cette équation-là. Donc pour démontrer l'existence, en fait, il faut commencer par démontrer l'existence de ça. Et ce qui se passe dans ça, c'est que essentiellement, ce qui est important quand epsilon est fixé, c'est l'opérateur de la chaleur, du dt moins epsilon d2u sur dx2. Ok. Ça, c'est un opérateur pour lequel on a des bonnes conditions. Donc si je mets égal à 0, par exemple, je peux écrire une formule explicite pour la solution. Si au lieu de mettre égal à 0, je mets égal à moins ça, je peux encore m'en sortir et démontrer l'existence de solutions. Donc c'est ce que j'ai affirmé ici. Il y a des solutions classiques qui existent pour cette équation et ça vient des propriétés des équations de la chaleur essentiellement. Il y a du travail à faire parce que là c'est non linéaire, mais ça se fait comme ça. Et une fois qu'on a cette solution, bah en fait on écrit ça, on fait tendre epsilon vers 0 et à la limite, on a un moyen de passer à la limite. Là aussi derrière il y a toute une théorie, il faut faire attention. À la limite, on obtient exactement cette information-là, et de cette équation, on obtient la formulation faible. Donc on obtient ces deux équations, et donc on obtient l'existence. Et ensuite, la théorie de Kruskov, ça en fait c'était connu bien avant Kruskov, la théorie de Kruskov, elle vous dit, cette condition-là, alors Kruskov en fait il mettait d'autres conditions, mais qui s'obtenaient de la même manière, en mettant à la place de u carré n'importe quelle fonction de u et en faisant la même chose. Mais en gros, cette condition-là, elle permet d'avoir une solution unique.
Maybe I was not paying attention. Like, was there some reason why we were? in the open questions, what was there some reason you're adding the random noise and asking those questions?
So, yeah, I'm sorry, I just spoke in French now, but I should have been speaking English. So, okay, one of the reasons is, as I said, somehow in real life you never have an equality. Things are never equal. They always come with some kind of random noise, some kind of thing that is perturbing them a little bit. So in real life there would be a noise if you want to actually model your thing completely. Then actually I gave you one example, but I can give you plenty of examples of stochastic processes that have this property that they converge to the Kruskov solution, and where you can ask this question and you don't know how to answer it. Another example is if you try to make a microscopic model of this. Instead of looking at your functions and density that are all continuous, you look at small particles, and they have a random rule for evolving, like they jump to the right with some probability, etc. And then if you do things correctly, you're going to see that they converge to the Kruskov solution. And then you can ask the same question. I mean, how can you estimate the rate of convergence? So that's another reason. Like this is okay. You think there is a noise anywhere. And another reason is if you want to go from a discrete description to your continuous description, you're going to face the same kind of issues.